So in today's lecture, we'll be discussing about the Langevin's classical theory for diamagnetism. So before that, we have to have a basic idea of what diamagnetic materials are. So in case of diamagnetic material, the susceptibility is negative. It can be either small or large. The susceptibility is negative and small, then it is temperature independent. Whereas if it is if the susceptibility is small, minus and large, then it will be independent of temperature below a critical temperature. Okay, below critical temperature it will be independent. So the examples are for small and negative susceptibility. The examples are just organic molecules, any polymer, silicon, germanium and all. Whereas in case of susceptibility being negative and large is superconductors. So this is the basic gist of diamagnets. The reason why the susceptibility is negative is because, okay, let's consider a case where a diamagnetic substance like silica is kept in an external magnetic field. The magnetization vector in the material will be in the opposite direction to the applied field. So the resultant magnetic field B within the material is less than nu 0 h. Nu 0 h is nothing but the applied field. So thus we can interpret this as magnetic substance is trying to expel the magnetic field from the material. And if the diamagnetic material is kept in a non-uniform magnetic field, then it experiences the force towards the smaller fields, and this repels the diamagnetic material from the permanent magnet. So these are the reasons why we can say that the susceptibility is negative, because it acts in the opposite direction. Okay. So I can write few notes. So this diamagnetic material, the susceptibility is due to Lenz's law. I'll write it as Lenz's law. Okay. And due to all these Lenz's law, there is a charge in the frequency variation. Let's dive into today's topic by considering a Bohr model of atom. Consider an electron which revolves around the central nucleus, and in absence of the magnetic field, the electron will have a centripetal force. So F is equal to mv square r, which is nothing but m omega naught square r square divided by r. V is nothing but r omega naught, which is equal to m omega naught square r. So in the absence of a magnetic field, the electron just experiences the centripetal force. Whereas if there's a magnetic field which is applied along the z-axis, then we will introduce the Lorentz force, Fl. So magnetic field is present in along z-axis. Fl is equal to E v cross B minus E v cross B, which is nothing but minus E br omega. As I said, V is nothing but r omega. You just have to substitute that. Now, because of the change in the net force on the electron, there will be change in the angular frequency as well. Because there is a change in the net force, there is a change in the angular frequency from omega naught to omega. So we can write it as absence of external field plus the presence of external field gives you a new angular frequency, that is mr omega naught square minus mr omega square is equal to ERB omega. Okay, now what you have to do is you can take the common terms. You get mr omega naught square minus omega square, which is equal to ERB omega. So gets cancelled. Finally so you have to solve this. This will be m omega naught plus omega and omega naught minus omega. That's nothing but omega naught square minus omega square, which is equal to EB omega. This term is nothing but 2 omega, and this term is nothing but omega L. So we can write it as m into 2 omega into omega L, which is equal to EB omega. And therefore omega L is nothing but EB divided by 2m. This equation is nothing but the Larmor frequency. Okay. Now from here itself we can get some solutions. We can understand few things. So from here, if I write it in the form of a second order differential equation, I can write this as m r omega square. I'll bring this term to the other side, m r omega square plus e r b omega minus m r omega naught square, which is equal to 0. Now bring this m r to the division, you will get omega square to be equal to this is plus EB omega divided by m minus omega naught square is equal to 0. And the solution to this equation is nothing but omega is equal to plus or minus omega naught minus omega L. So the solutions are minus omega naught minus omega L and plus omega naught minus omega L. Okay, so if it's minus omega naught minus omega L, the moments are anti-parallel to the field. Moments, how do you write anti? Moments are anti-parallel. Whereas in this case, one is positive, one is negative, we will get moments are parallel to the field. Okay, yeah. Now what we can find is we can find current. Current is nothing but charge into revolutions per unit time. So charge into revolutions per unit time gives you minus E into omega by 2 pi. And this is omega L, okay. And substitute the value of omega L to here, you will get, you just have to substitute EB by 2m again, you will get minus E square B by 4 pi m. And magnetic moment U is equal to I cross A. So here you can take two conditions, okay, fine. So wait, this one I'll take current to be minus E square B by 4 pi m into pi r square. So this becomes minus E square B r square by 4 pi m, yeah. Okay. Instead of writing like this R, we can use rho square, which is a mean square radius of the projection of an orbit. So in order to define R, we'll take a great circle and we'll draw some orbit inside it. Okay, so here you can see that rho square is equal to x square plus y square, whereas r square is equal to x square plus y square plus z square. It said that in the absence of the field, the electron motion will be spherically symmetrical. So we can say that x square plus y square, x square is equal to y square is equal to z square, and therefore r square is equal to 3x square, and rho square is equal to 2x square. So the average radius rho square can be written in terms of r square, like you just have to equate this, you will get 2 by 3 r square. So this is the average radius in terms of radius. Now instead of this thing, we can, instead of using pi r square, we can use pi rho square, and rho square is nothing but 2 by 3 r square, and you will get the nu. Okay, so you just have to find that. So the equation for nu was nothing but I cross A. We found I to be, I guess, minus e square, yeah, minus e square b by 4 pi m into pi rho square and minus e square b by 4 pi m. Pi gets cancelled, so just write that 4m. 2 by 3, okay, 2 by 3 ka 2 goes, so r square pi 3, which is equal to 6. So this is it. This is nu b. And in order to find susceptibility is nothing but m by h. M is nothing but n nu b divided by h. So can say this as n minus n b square, this thing br square divided by 6mh, where b is nothing but nu 0 h. So it's like there are so many terms you have to remember. M is n nu b, b is nu 0 h. Then what else is there? Permeability is b by h. Susceptibility is m by h. So there are a few terms you have to remember, for few things you have to remember. So instead of b, we will substitute nu 0 h. So my this time nu n e square nu 0 r square divided by 6m. So minus, okay, yeah. So this is the classical Langevin equation for diamagnetism. It's very simple. You started in with the case where there is no magnetic field, so there is only centripetal acceleration for an electron orbiting the nucleus, and then when you apply external magnetic field, you have a Lorentz equation. You just have to equate these two when there's case where there's magnetic field without magnetic field into a new angular frequency. So you just have to solve this. You'll get for Lama precision, this is Lama frequency EB by 2m, and this is a solution. And from this solution, you'll understand if the moments and fields are parallel or anti-parallel. And next, from using this Lama precision, you'll find I, and with that I, you find nu. Nu is equal to I cross A, and here in case of pi r square, you can write it as pi rho square, which is a mean square radius. So in order to find rho square, you do this diagram. This is the projection, and then rho square is from here. We will understand rho square is equal to x square plus y square, and then r square is x square plus y square plus z square, and then you just substitute it and you'll get the value for rho square in terms of r square. And then again, you, instead of using r square here, you use rho square and substitute the value. You'll get like this. So you got nu b. From that you can find susceptibility, which is nothing but m by h, and m is nothing but n nu b. You substitute it, and in that you get b. B is nothing but nu 0 h, and you just substitute that and you'll get the final equation. And this is the classical Langevin equation for diamagnetism. That's all for today. See you in the next one.